Intelligent machining. The current period known as Industry 4.0 is realizing the transformation from manual to digital operations, and it has significance to manufacturers throughout the world. We are in the era of digital manufacturing and design, or VMD. The concept of intelligent machining, or IM, and what it means within the context of digital manufacturing and design paradigm. Processes, previously monitored and controlled by humans, are now being controlled and monitored by smart sensors and actuators in this new generation of manufacturing. Intelligent machines use sensors and data to determine various aspects of manufacturing processes to maximize operations efficiency. The outcome: high productivity, high quality, significant improvements to manufacturing processes, enhanced communication among stakeholders, smarter decisions, shorter product life cycles, and superior data interoperability. Let's explore how data-driven machine learning algorithms can help detecting problems in complex and uncertain manufacturing environments. We have made significant progress in manufacturing, and intelligent machining signifies how automation can benefit those in the industry. Reiterating the mantra of this specialization, it's having the right information in the right place and at the right time. We will see how intelligent machining can help make companies more agile, more productive, and more competitive. Intelligent machining is an integral part of the digital manufacturing paradigm. You will be able to state components required to enable the intelligent machining in the manufacturing workflow. And finally, you will have the basics to enable you to participate in planning and execution of an intelligent machining project in an industrial setting. Let's embrace the new opportunities technology brings to manufacturing as we explore intelligent machining in this course of the Digital Manufacturing and Design Technology Specialization. Machining Basics. The concept related to the intelligent machining paradigm. We will be focusing on two components of intelligent machining: sensing and control. Describe the conceptual framework of intelligent machining. List the three phases of the evolution of intelligent machining. Let's focus on the concept of machining first. Machining is a process, therefore, like many other processes, it has an input and an output. The input to the machining process is raw material, which might be metallic or non-metallic. The output of the machining process is a finished product of desired shape and size. Machines, tools, and workpieces are the main components of the machining process. More formally, machining is a broad term used to describe different removal processes of unwanted material from a workpiece in the form of chips to arrive at a desired final shape and size. As metals are still the most widely used materials in manufacturing, machining processes that remove material from metallic workpieces are the most important class, and are tone metal cutting, or metal removal processes. The counterpart of metallic machining processes are non-metallic machining processes that use non-metallic workpieces made of materials such as wood, and another classification of machining processes is based on the differences between the relative motion of cutting tool in the workpiece, and the type of cutting tool used. In turning operation, the workpiece is rotated as the primary method of moving metal against the cutting tool. There, our primary machining tool for performing turning operation. Second, milling. In milling operations, the cutting tool rotates to bring cutting edges to bear against the workpiece. Milling machines are primary machines tool for performing mill. Third, drilling. Drilling is a machining operation that is used to produce hole or bore features in a workpiece. Drill presses are the primary machine in this category. Abrasive processes are another class of manufacturing processes that remove material by forcing hard abrasive particles onto the surface of workpieces. This process groups include grinding, and other processes such as finishing. Finally, there also exist non-traditional machining processes in which other forms of energy other than sharp cutting tools such as water jets and laser plasma are used to remove material. The evolution of intelligent machining. The evolution of intelligent machining can be grouped into three major phases. Phase 1, from the year of 1700 to 1900. During this phase, hand tools were transformed into mechanical tools. This transformation was enabled by using mechanical principles, and the machining was performed in a much more efficient way. Phase 2, from the 1900 to 2000. Machine tools based on mechanical principles are transformed to digitally controlled machine tools. Constraint conditions and performance functions were given to machine to get desired output. This allows for multifunctions and feedback of cutting processes. This was the era of CNC machine. Phase 3, from the year 2000-present. The transformation of newly controlled CNC machines with adaptive controls to intelligent controls. In this phase, the sensors are used to receive automatic feedback from the machine tools. And use machine learning algorithms allows for optimizing future operations. This leads to increased productivity and automatic decision-making. Components of intelligent machining. Advances in sensor technologies and automated data systems provide new opportunities for real-time collection of valuable measurements that can be converted into actionable information to make smart decisions. The data acquisition and management module is comprised of the data aggregator component, a data post-processor, and a data buffer component. The data aggregator component collects time-synchronized raw data from external sensors. Since the data generated from different sensors can be in different formats, they need to be transformed into single format to enable it to be processed into information. Data aggregators allow for this interoperability. Empty Connect is an example of industry-standard data aggregation agent that allows for data aggregation. Data processor processes the collected data into suitable data formats that can be used by machine learning algorithms to make smarter decisions. Whereas, data buffer allow for data buffering so that the unwanted data can be erased at this point. The data buffer stores only relevant data that could be used by machine learning algorithms to generate actionable intelligence. Data buffers act where in between the data processing and machine learning algorithms and allows for efficient storage. The Data Dividend Machine Learning and Knowledge Discovery module uses the processed monitoring data to construct a data dividend prediction model for the target machine. The prediction model is used in conjunction with the data from past experiences to monitor and control the machining tool.